This video is going to be an introduction to what Iwasawa theory is. So Iwasawa theory is a branch of algebraic number theory that's devoted to doing number theory in infinite towers. So here's the basic philosophy of this whole area. Generally in number theory, we study arithmetic objects that are defined over a single number field. Right? So for example, if you have a number field k, you might ask, okay, what is the class group of k? On the other hand, in Iwasawa theory, we don't look at one number field, we look at an infinite tower of number fields. Infinite tower of number fields. So we might ask, for example, if you have a tower of number fields, k1, k2, k3, on and on, you might ask, how does the class group of kn grow as n goes to infinity? And the general philosophy is that this can often be quite hard. I mean, if you just have one number field, what can you really say about this? But on the other hand, this can be considerably easier to answer, even though a priori, it seems like, well, you have to study more number fields. But somehow, this ends up being a lot easier to answer in some cases than this one. And then you could use information over here to descend down to get information about each individual layer in the tower. So the first proof of concept of this was given by a theorem that's due to Iwasawa, which sort of serves as the fundamental theorem in this whole subject. So here's what the theorem says. Consider the following tower of number fields. We're going to let p be a prime number, and we'll look at q zeta p. This is the cyclotomic field of pth roots of unity. Zeta p is e to the 2 pi I over p. This sits inside q zeta p squared, q zeta p cubed, on and on. These are the p power roots of unity. And we're going to let pn, p to the en, be the exact power of p dividing the class number of q zeta p to the n. Okay? The theorem says there exist integers mu, lambda, and nu such that en equals mu p to the n plus lambda n plus nu for all n. Okay, so this is what this theorem says. Now, this is a really amazing theorem because nobody knows how to compute class numbers. If you try to actually compute the class number of q adjoint zeta p to the n using, say, Minkowski's bound, it just won't work because this has really large degree over q. So Minkowski's bound just is not practical. So the fact that you can say anything at all about these class numbers is really quite amazing. But Iwasawa was able to say something about these class numbers in one shot when you arrange them in an infinite tower. So that itself is really quite remarkable. I should say, however, this theorem only tells you about the class number. So it doesn't tell you about the group structure of the class group, but only the class number. Nevertheless, it's still a really beautiful theorem. So let's look at some numerical examples of this to get a feeling for what it is saying. So as an example, before that, let's already state a corollary, which is non-trivial. If p doesn't divide the class number of q zeta p, then p doesn't divide the class number of q zeta p to the n for all n. Right? And the proof of this is that, well, if this holds, that means in the previous theorem, mu, lambda, and nu are all equal to 0, in which case en is equal to 0 for all n, which precisely means this. Right? So as an example, this hypothesis over here holds if p is any prime less than 37, for example, because you can just calculate these class numbers, and this is true. So therefore, we immediately get this hypothesis over here. Already this is highly non-trivial and highly non-obvious. Okay. So as we saw, this is already our first numerical example. So here, mu, lambda, nu are all 0. Let's look at another example. Let's say p equals 37. What happens then? So it turns out the class number of q adjoint zeta 37 is 37. So in this case, one can show that mu is 0, lambda is 1, n nu is 0. So in other words, En is n for all n. So En is the exact power of 37 dividing the class number of q adjoin zeta 37 to the n. Okay? So that's what this says. So what I want to do in this video is explain how one proves Iwasawa's theorem, right? Because the proof is really beautiful, and it sort of sets up a general strategy as to how to even prove number theoretic statements in infinite towers of number fields. So the notation that I'll use is Kn. I'll use it to denote the nth layer of the tower, just to save on notation. And I'll say Xn is the P CELO subgroup of the class group of Kn. Okay, so in this notation, P e to the n is simply the size of Xn. So we want a formula for the size of these groups over here. So let's draw this in a picture. We have K1, which is, I'll just write this as K, Q adjoins zeta P, K2, K3, on, and then over here we have X1, X2, and X3. Okay. Now, it's a general fact that we'll use if you have any Galois extension, L over K, of number fields. Yeah? There's a norm map from L cross to K cross, right? Given any element here, you send it to the product of all its Galois conjugates, and that's Galois invariant, and that lands you over here. And this induces a map from the class group of the top field to the class group of the bottom field. So namely, this is the natural map. Given an ideal class, say, of an ideal frac alpha, this just sends you to the ideal class of the product over all Galois element sigma of alpha sigma. And that gives you something down here. Okay? So this is the norm map. We'll also call this norm from here to here. And another thing that we're going to use is, given the same setup, the Galois group acts on the class group of the top field. And again, this is the natural action, right? So given sigma over here, and given an ideal class over here, sigma acts on alpha just by, sigma acts on frac A just by doing this. Okay? Okay, so let's apply this scenario to this thing over here. So this has an action, how do we write this? So going down all the way here, we have the norm maps, which I'll just write as n, right? Norm from here to here, norm from here to here, norm from here to here, and this sort of continues. And then Xn has an action of the Galois group of Kn over K, right? So Kn is something over here, Galois group of Kn over K. You might say, okay, Kn is zeta p to the n. Is Galois over Q, in fact? So can't we use gal Kn over Q? I mean, we can, but in this proof, we actually only need the fact that it's Galois over K. That's the only thing we're going to need, so that's what we're going to do. Okay. Okay, so this is the essential number theoretic input that we're going to need for our proof. So let's use that. So Xn, let's rephrase what we have in the language of commutative algebra. So Xn is a z bracket gal Kn over K module. Okay, what does this mean? Well, first of all, it's an abelian group, right? So it's a Z module. And furthermore, it has an action of this Galois group. So this is the group ring, Z bracket gal Kn over K. So this is just rephrasing what we saw in the previous page. But we can actually do a little bit better. Not only it's actually, in fact, a ZP bracket gal k n over k module. This is the ring of p-adic integers. And this is because this is the p part of the class group of the nth layer of the tower. So it's an abelian p group, right? So in fact, every abelian p group can be thought of in a natural way as a ZP module, not just a Z module. So it's a module over this thing. Great. So as I said before, we have all of these xn's and they're connected by these norm maps. So in Iwasawa theory, it's advantageous, and we'll see in the proof, it's crucial to consider all of the xn's at once in one shot. Okay? So we're going to look at the inverse limit of these xn's, where the inverse limit is taken with respect to the norm maps that we saw before. Okay, and I'm going to denote this thing by x infinity. Now, x infinity is our fundamental object of study in this proof. More than the xn's, we're going to really study x infinity. So this thing, it is a inverse limit ZP gal kn over k module. Because each xn is a module over this, so the inverse limit of the xn's is a module over the inverse limit of these group rings. Okay? So x infinity is a module over this. Okay, so when you look at this, you're sort of like, I don't know what this thing is. This is a very mysterious ring. How do we even understand it better? Luckily, there is a very nice theorem which gives us a nice structure for this. So it says, there is an isomorphism between the inverse limit of ZP bracket gal kn over k and the power series ring ZP double bracket T. Okay? This is the ring of formal power series with coefficients in ZP. Now, luckily, this is a very nice ring. We can write elements down, and it's very concrete, and this is kind of mysterious, but we understand this. So because of that, this x infinity is actually a ZP double bracket T module. Is a ZP double bracket T module. Now, for the rest of the proof, we're going to forget the fact that x infinity, we're going to forget the definition of x infinity as an inverse limit of these class groups. We're only going to remember the fact that x infinity is a module over the power series ring. And with that, we're going to complete the proof. Okay, so we now want to study modules over this ring and use tools from commutative algebra to do that. Before we do that, I want to recall a very nice theorem from just normal commutative algebra, which says the following. If R is a PID, a principal ideal domain, and M is a finitely generated R module, then M is isomorphic to R to the N, direct sum R mod A1, R mod AK, where these AIs are just elements of R. Okay? So this is just a classical theorem. In the case where R is Z, this is the fundamental theorem of finitely generated abelian groups. It's in like Dummett input. Now, if ZP double bracket T was a PID, we could just plug and play with this structure theorem and apply it to our module x infinity. However, ZP double bracket T is not a PID. It's not a PID. And as an example of this, the ideal P comma T is not principal. Right? So we cannot apply this theorem directly. However, there's a very nice result due to Serre, which says that there is even though it's not a PID, there is a decomposition theorem that's highly analogous that we can use. So this is Serre, and this is often called the structure theorem for ZP double bracket T modules. Okay, so here's what it says. If M is a finitely generated ZP double bracket T module, then we can write M as ZP double bracket T to the R, direct sum I equals 1 to S of ZP double bracket T modulo P to the EI, direct sum J equals 1 to T of ZP double bracket T modulo Fj. Okay, so there are a few things that need to be explained here. The EIs are just they're just like non-negative integers. The Fj's are so-called distinguished polynomials. Distinguished polynomials. So a distinguished polynomial is a polynomial such that it's a polynomial in ZP double bracket T such that if you reduce it mod P, only the highest degree term remains. So something of the form A T to the N plus P times lower order terms. Okay, and A is a p-adic unit. By lower order terms, I mean like T to the N minus 1 and lower order in degree. All of these terms are 0 mod P. Okay, great. So there's one thing I still have to explain, and that's this sign over here. This is not an isomorphism, but it's something a little bit weaker called a pseudo-isomorphism. So when M and N are ZP double bracket T modules, this means that there is a map phi from M to N such that the kernel of phi and the co-kernel of phi are both finite. Okay? So of course, if M and N are literally isomorphic, then they're also pseudo-isomorphic because kernel of phi and co-kernel of phi are 0, so they're finite. But this is a slightly weaker notion. It means that M and N are like equal up to a finite amount of discrepancy. Okay, so this is the full statement of the theorem. And this is very analogous to the structure theorem for finitely generated modules over a PID. With this in hand, let's apply this to our module x infinity. So to do that, we need to show that x infinity is finitely generated as a ZP double bracket T module. So we're going to use the following fact that for now we're going to take as a black box. X infinity is finitely generated and torsion as a ZP double bracket T module. Okay. Now that we have this fact, we can apply this theorem and we can get this result for x infinity. So x infinity is pseudo-isomorphic to ZP double bracket T to the R, direct sum I 1 to S, ZP double bracket T mod P to the EI. J goes from 1 to T of ZP double bracket T mod Fj, where these are non-negative integers and the Fj are distinguished polynomials, and this is a pseudo-isomorphism. Okay, now to get this, you only need the fact that it's finitely generated. So how are we going to use the fact that it's torsion? Torsionness precisely means that this term does not exist, right? There's no, so R is 0. So it's actually just this finite part, or I shouldn't say finite. It's just this torsion part over here. Great. So we have this abstract result about x infinity, but we actually want to study xn, which is the p part of the class group at the nth layer of the tower. How do we transfer this information from x infinity down to xn? So to do that, we need the following key proposition, which is not too hard to prove. But it says that xn is isomorphic to x infinity modulo the following submodule, 1 plus t p to the n minus 1 x infinity. Okay? So this is an ideal of zp double bracket t, the ideal generated by this polynomial. So we can, take our module and apply this ideal that gives you a submodule. We can mod out by that submodule, and then the claim is that equals xn. Okay? So every xn is just a quotient of x infinity. Okay. So with this in mind, let's prove our theorem. Okay. So for now, let's pretend, we'll remove this assumption in a bit. Let's pretend that this is actually an isomorphism. It's not actually true that this is always an isomorphism. So let's pretend it for right now, and we'll remove that assumption later. So if we do that, what's the size of xn? Okay, so this is just a calculation. Xn is just this, that's x infinity, modulo this. So let's calculate what that is. So it's the size of the direct sum over all I of zp double bracket t modulo p to the ei modulo this polynomial. Okay, times the size of the direct sum over all j of zp double bracket t modulo fj modulo that polynomial. Okay, so this is purely a commutative algebra exercise. Okay, it's kind of tricky to calculate the sizes of all these things, but it can be done. It is purely commutative algebra, and I won't do that here. But if you do that, you'll find that the size of this is p times the sum of all these ei's times p to the n. So this ei is the same as that ei. And the size of this is p times the sum over all the j's of the degrees of the polynomials fj times n. Okay, and this is a finite sum, right? This is a finite direct sum, so these are finite sums. Great. So we're going to call this quantity mu, and we're going to call this quantity lambda. So this equals p mu p to the n plus lambda n. And this is essentially Iwasawa's theorem, right? It says that the size of the class group at the nth layer is given by p mu to the p to the n plus lambda n, but there's an extra term plus nu. So where does this nu come from? Well, remember, we pretended that this was an isomorphism, but actually it's not. It's a pseudo-isomorphism. So there's this is equal to this plus a bounded amount which does not depend on n. So if you carry out those details, that bounded amount gives you this extra term nu over here, which reflects the fact that it's a pseudo-isomorphism and not an isomorphism. Okay? But that is a sort of high-level sketch of how you prove Iwasawa's theorem. Now, I should say, just to summarize how this proof goes, what did we do? So xn was the p part of the class group at the nth layer of the tower. We looked at the inverse limit of those with respect to the norm maps, and that gives you x infinity. X infinity was a module over zp double bracket t, and we asserted, without proof, that it's finitely generated in torsion. Therefore, applying the structure theorem, it's pseudo-isomorphic to this stuff. This proposition tells us xn is a quotient of x infinity. Therefore, we can calculate the size of xn by calculating the size of these various things, And when we do that, Iwasawa's theorem just pops out. Okay, that's how this proof goes. Now, it might feel like we sort of got something for nothing because all we really used was that x infinity is a module over this power series ring. So where is the number theoretic input that we use in this proof? Really, it seems like this proof is just commutative algebra. The key number theory input was in this fact over here. How do you actually show x infinity is finitely generated in torsion? Now, showing it's finitely generated isn't too hard. You use Nakayama's lemma. But showing its torsion is considerably harder. And the key input is the fact that xn's are all finite. And the reason the xn's are finite is because the class group of any number field is a finite group. And that's a highly non-trivial number theoretic theorem that uses the geometry of numbers to prove and whatnot. So that's where all the number theory input goes in. You use the finiteness of class group to show that it actually must be torsion as a ZP double bracket T module. Okay? But if you do that, you get Iwasawa's theorem over here. Okay? Thanks for watching. I'll see you next time.